Most people who find one of these on their porch light think they've stumbled onto something prehistoric, and honestly, they're not wrong to be startled. This thing is about 6 centimeters long, built like a tank, with front legs designed to grab and hold prey, and a beak that dissolves tissue from the inside out. But here's what nobody tells you. It didn't come to your porch because it wanted to. Your light pulled it out of the swamp, away from the frogs and insects it actually eats, and dropped it right at your feet. If you sat down to design an underwater ambush predator from scratch, what would you actually build? Think about it for a second. You'd want something that can stay perfectly still, strike faster than the prey can react, and then process a struggling animal without losing it in the water. Whatever you sketched out, Lithosaurus americanus already built it, and it did so a very long time before we started paying attention. Start with the front legs. They're raptorial, which means they don't reach and grip the way a crab's claw does. They snap shut, like a trap springing closed, and the timing on that snap is fast enough to catch a frog mid-kick or intercept a small fish that's actively trying to escape. That's not a small thing. A frog kicking to get free generates real force, and the leg has to close before that force becomes a problem. Most people assume a bug this size works the way a wasp or hornet does, by injecting venom to stop the prey fast, and then dealing with it afterward. But Lithosaurus americanus doesn't do that. The front legs hold. Then the rostrum does something else entirely. The rostrum is that short, curved beak you'd notice right away if you looked at one up close. It doesn't chew anything. What it does is inject digestive enzymes directly into the prey's body, and then the bug draws the liquefied tissue back out through the same beak. The prey gets dissolved from the inside while it's still being held. From a practical standpoint, this is a more efficient system than teeth or mandibles for an aquatic animal, because nothing washes away in the water, and the bug doesn't have to keep wrestling a live animal for long. The chemistry does most of the work. So the legs and the rostrum aren't two separate tools. They're one system that runs in sequence. The legs immobilize, the rostrum processes, and neither step works without the other. That coordination is what lets a 6-centimeter insect pull apart prey many times its own body weight without losing control of the situation. Consider what that looks like in an actual wetland. This bug sits motionless in the submerged vegetation, waiting, and then it locks onto a frog that could kick free of most things trying to hold it. The grip has to be immediate and total. If it isn't, the whole feeding sequence falls apart before the rostrum even makes contact. What the data shows is that giant water bugs aren't just opportunistic feeders picking off weak or slow prey. They actively suppress populations of aquatic insects, tadpoles, and small vertebrates in ways that keep wetland food webs from tipping out of balance. Pull them out of a pond system, and you'll likely see those populations spike in ways that ripple through the rest of the web. That job depends entirely on the bug staying in the water, and that's where our story gets complicated. Giant water bugs fly. That's the part most people don't know, and it's the part that explains everything about why one ended up on your porch. They're strong flyers, and they move at night, navigating between wetland patches by reading reflected light off water surfaces. That system worked for millions of years. Water reflects light in a specific way, and the bug's visual system is tuned to follow that signal from one pond to the next. A porch light doesn't reflect the same way a pond does, but it doesn't have to be a perfect match. It just has to be close enough, and for Lithosaurus americanus, a lot of artificial light sources are close enough. Parking lot lamps, lit windows, security lights mounted on the side of a barn. These all produce light that the bug's visual system reads as water. It's not that the bug is broken or malfunctioning. It's doing exactly what it evolved to do. We just built things that mimic the signal it evolved to follow. Researchers who study artificial light at night, a field they abbreviate as ALAN, call this a sensory trap. The animal responds correctly to the stimulus it detects. The stimulus is just wrong, and white light makes this dramatically worse than amber or yellow light. Studies comparing white LED traps to amber-filtered traps in field conditions found that white light pulled in roughly 60% more insects overall and captured 34% more species. The blue-white spectrum of a standard LED bulb matches the reflected light cues that nocturnal insects use for orientation far more closely than longer wavelength amber light does. So when a giant water bug leaves a wetland, crosses open air, and lands on your concrete driveway, that's a predictable outcome of a specific light wavelength hitting a specific evolved response. Nothing went wrong in the bug's decision-making. Your light outcompeted the wetland. Once it lands on dry ground, the bug can't easily reorient. It's built for water, and on pavement or a porch, it's exposed, losing moisture fast, and burning energy it would otherwise spend on feeding and reproduction. A lot of them don't make it back to the water. What makes this predator so effective isn't speed, it's deception. The giant water bug doesn't chase prey through the swamp. It waits for prey to come willingly. Many aquatic insects use light reflections to stay oriented near water. Moonlight bouncing off ponds and wetlands normally creates visual cues that tell them where it's safe to land, mate, or lay eggs. But the beetle has learned to exploit that instinct. When insects gather around bright surfaces or artificial lighting near water, the giant water bug positions itself nearby and waits. To the prey, the glow feels familiar, something that signals open water and safety. But what they're really flying toward is a feeding zone. The mistake happens fast. An insect drops lower, circles the light source, becomes distracted by dozens of others doing the same thing, and suddenly enters striking distance. The giant water bug lunges, grabs with hooked front legs, and drives its needle-like mouthpart straight into the body. No long chase, no warning, just an ambush triggered by a false signal. That's what makes this hunting strategy so effective. The beetle doesn't need to create the trap, it just waits beside it. And when the same false signals appear night after night, across wetlands, docks, and waterfront paths, predators gain a hunting ground that never really turns off. The giant water bug's hunting strategy works because it hijacks a rule insects have followed for millions of years. Reflected light usually means water. Many flying insects don't see ponds and wetlands the way we do. Instead, they detect polarized light, light waves reflected off smooth surfaces in a specific pattern. Water naturally creates that pattern. For countless insects, that reflection acts like a built-in map, telling them where it's safe to land, mate, lay eggs, or escape predators. The problem is that artificial light and reflective surfaces can mimic those same signals. To an insect flying at night, a bright reflection near water, or even concentrated light spilling across a surface, can look close enough to the real thing. The prey isn't making a random mistake. It's following survival instincts that normally work, and the giant water bug takes advantage of that confusion. Instead of actively chasing prey through dark water, it waits where those insects concentrate. Around these false signals, insects slow down, circle, hover, and cluster together. What should have been navigation becomes predictability. That predictability is the trap. A mayfly dropping lower toward what it thinks is water. A beetle circling a reflection one too many times. Even fireflies, which use light signals to find mates, can become distracted when artificial light interferes with the cues they evolved to trust. The moment prey enters range, the giant water bug strikes. Hooked front legs lock prey in place. The piercing mouthpart follows. The hunt is over in seconds. That's what makes this predator so effective. It doesn't create fake signals itself. It simply waits beside mistakes that other species were biologically programmed to make. None of this asks for a major investment. It's applying what the data shows to hardware you already own or will replace anyway. When a giant water bug lands on your porch, It's telling you your light reached far enough to pull a specialized wetland predator off its hunting ground. Changing the bulb is the direct response to that information. Lithochorus americanus didn't evolve to end up on your porch light. It evolved to hold a wetland food web together, eating everything from aquatic insects to frogs. And it's been doing that job far longer than we've had electricity. The law says monster. The data says your light is the problem. If you manage land near a pond, a ditch, or any wet area, the insects working that system are doing biological control you'd otherwise lose entirely. Keeping them in the water starts with one amber bulb. Save this to your reference playlist before your next property improvement season, because the lighting decisions you make this year run every night for years.